Hello, welcome to Module 4 of the course on application of spectroscopic methods in molecular structure determination. In this module, we will continue with the NMR spectroscopy and we will actually see some NMR spectra of very simple organic compounds. We will try to interpret the spectrum of these compounds and see whether we can familiarize ourselves with the chemical shift and the coupling constant values. Molecular structure determination by NMR spectroscopy is all about pattern recognition. There are certain patterns which appear in the NMR spectrum. If one can recognize this pattern and identify the structural element or structural feature that is responsible for the pattern, then it solves the problem of structure elucidation. Let us start with a very simple example. Ethyl bromide is what is shown here. The spectrum of ethyl bromide. Ethyl bromide contains a CH3 and a CH2 group. So the CH3 will be appearing as a triplet because it will be split by the adjacent two hydrogens of the CH2. So this triplet is appearing in the region of 1.6 ppm or so. And the CH2, which has three hydrogens which are adjacent to it, will be split into a quartet. So one observes a quartet around 3.5 ppm or so. Now the CH2 is directly attached to an electronegative bromine. That is the reason the chemical shift value of the CH2 is much higher than the chemical shift value of the CH3. If one measures the intensity ratios of these two or the area under the peaks of these two multiplets, it would correspond to 2:1, 2:3 corresponding to the CH2 and the CH3 groups. You also notice the pattern which is a quartet with an intensity ratio of 1:3:3:1 and the triplet as 1:2:1. There are some distortion which are actually explained as a second order effect, which you will see at a much later stage. This is a spectrum of propionamide. The purpose of showing the spectrum of propionamide is to illustrate that hydrogens which are NH2 and OH would appear normally as broad peak in the NMR spectrum because of their exchangeable nature. The chemical environment of the exchangeable nature of hydrogen is uncertain. So as a result, there is some uncertainty associated with the chemical shift value of this hydrogen. That is why they appear as broad signal here. In this particular case, the broadness may be due to another factor, that the hydrogens are attached to a nitrogen nucleus. Nitrogen is a quadrupolar nucleus. Quadrupolar nucleus also give broadening effect in the NMR spectrum. The way to identify this peak to be the NH2 peak is to do a deuterium exchange experiment. In other words, if you take the sample and add a drop of deuterium oxide and then measure the NMR spectrum, the NH2 hydrogens will be exchanged by deuterium to ND2. As a result of that, the peak due to the NH2 hydrogens will be completely lost after the deuterium exchange during the experiment of deuterium D2O addition to the sample. Otherwise, the spectrum is fairly routine and simple. You have a ethyl group which is recognized by this pattern of quartet and a triplet. Please notice that the chemical shift value of the CH2 here, which is adjacent to a carbonyl functional group, which is about 2.2 ppm. Anytime a CH2 or CH3 group is adjacent to a carbonyl functional group, this is the region in which the CH2 or CH3 adjacent to the carbonyl group would appear in the NMR spectrum. This is a spectrum of benzyl acetate. It's a simple ester compound. You can see here the phenyl hydrogens are appearing in the region of about 7.3 ppm. Sorry, the chemical shift values are not given here, but I will tell you that this is corresponding to about 7.3 ppm and this CH2 singlet corresponds to about 5.5 ppm or so, whereas the CH3 corresponds to about 2.1 ppm or so. Now the CH3 does not have any partners to couple with. As a result, it appears as a singlet of 3 hydrogen intensity. Similarly, the CH2 also does not have any partners which are adjacent hydrogens. So it appears as a singlet around 5.5 ppm or so. The mono-substituted benzene phenyl derivative should have appeared as a multiplet because the ortho, meta and para hydrogens are not chemically equivalent. They should have given 3 different chemical shift values. However, the CH2 group is not a strongly perturbing group. It is not a strongly electron donating or an electron withdrawing group. So it is only a carbon based substituent, does not have much of an electronic influence on the phenyl derivative. So as a result of that, the ortho, meta and para hydrogens accidentally come in the same chemical shift region, appearing what appears to be a singlet for the case of the phenyl derivative. Normally, a phenyl derivative with electron withdrawing group or electron donating group, such as nitro group or amino group, would appear as a multiplet in the region. Anytime in the aromatic region of about 7 to 7.5 ppm, a multiplet is observed with 5 hydrogen intensity, the inference is that it is a monosubstituted phenyl derivative. This is a spectrum of ethyl formate. The formyl group hydrogen essentially comes at a higher delta value of about 8.1 ppm in this particular case. This is because of the anisotropic effect of the carbonyl functional group, which pushes the chemical shift value all the way up to 8 ppm in this particular case. Otherwise, the spectrum is fairly simple. You can see here this is an ethyl ester. The ethyl ester essentially appears as a quartet and a triplet. Notice the chemical shift value of the CH2, which is directly attached to an oxygen functional group. Whenever the CH2 group is attached to an oxygen functional group in the form of an ether, it will be less than 4 ppm. If it is attached to an oxygen in the form of an ester, it will be more than 4 ppm. In this case, it is about 4.1 ppm is the chemical shift value of the CH2 that appears in the spectrum. Let us try to solve a simple problem here. This is a compound with a molecular formula C4H8O. If you look at the molecular formula, it gives you an information regarding the unsaturation that is present in this compound. For a saturated molecular formula, this should have contained 10 hydrogen, but there are only 8 hydrogens in the molecular formula, so the degree of unsaturation corresponds to 1. This is important information we will make use of in the logical detection of the structure of this particular compound. Now, looking at the NMR spectrum, one obviously refers to this quartet and a triplet and infers that there is an ethyl group that is present here, and looking at the singlet of 3 hydrogen intensity, one infers that there is a methyl group present in this system. So the compound essentially contains one methyl group and one ethyl group, and if one subtract these fragments from the molecular formula, what will be left with is a CO functional group, which is a carbonyl functional group, and it is probably CH3CO, CH2CH3. In other words, it is ethyl methyl ketone is what we are referring to, or 2-butanone is what we are referring to. Now notice that the CH3 and the CH2, which are adjacent to the carbonyl functional group, comes in the typical region between 2 to 2.5 ppm chemical shift value. You also notice that there is no coupling between this CH3 and the CH2 because of the intervening carbonyl functional group, which acts as an insulator. So normally you don't see any kind of a coupling across the carbonyl functional group of the 2 hydrogens which are attached to the carbonyl functional group. This is again another simple molecular formula, except this has one oxygen more than the earlier example. The earlier example was C4H8O, and this is C4H8O2. Now if you look at the spectral pattern, it looks similar to the spectral pattern we saw earlier in the earlier example. The earlier example, you had a quartet, triplet and a singlet of intensity 2:3:3. Here also you have a quartet, singlet and a triplet, and approximately the intensity ratio, take it from me, it is about 2:3:3. So this molecule also has an ethyl group and a methyl group, but then it has one extra oxygen, so most likely instead of a ketone this could be an ester. How do we identify this to be an ester? Look at the chemical shift value of the CH2 hydrogen. The CH2 hydrogens come around 4.2 ppm. The earlier example, the CH2 hydrogen, which is adjacent to the carbonyl functional group, came around 2.5 ppm. Now because it is an ester type of a molecule, the CH2 is attached directly to the oxygen, which in turn is attached to the carbonyl functional group. So anytime you see a quartet above 4 ppm, one can infer that it is about ester functional group. Ethyl ester functional group is what is being inferred from this quartet and the triplet in the NMR spectrum. So this is essentially the spectrum of ethyl acetate, which is a very simple molecule. Let us go into a little more complex problem. If you look at the molecular formula here, the molecular formula, saturated formula, should have had 12 hydrogen. Now nitrogen is trivalent, so one has to subtract 1 hydrogen from the available hydrogen. Instead of 7, it would become 6 because of the trivalent nature of oxygen. So instead of 12 hydrogen, this molecule has the equivalence of about 6 hydrogens only. That means the degree of unsaturation of this particular molecule is 3. Now look at this pattern, essentially same as the previous pattern that you saw, except that you have a integration difference here. Now what is this integration? The line that is shown here essentially represents the area under each of these peaks. This height starting from here, this particular height is what is referred to as the area under this peak, integration under this peak, and starting from this base up to this point, this height is essentially the integration of this particular hydrogens, and this height is integration of this particular multiplet signal. If you look at carefully, this integration height and this integration heights are essentially same. This is because of a CH2 hydrogen, because it is a quartet, so this is also most likely a CH2 type of a functional group. See that the CH2, actually the multiplet quartet, comes above 4 ppm. So once again it is most likely an ester functional group. So it is an ethyl ester. So what we have identified as structural feature is COOC2H5 and a CH2 group. Now if you subtract the COOC2H5 and a CH2 group from the molecular formula, what will be left with is a cyano-functional group. So if you look at the CH2, this should be di-substituted. CH2 obviously had to be di-substituted derivative. So one substituent probably is a COOC2H5, the other substituent probably is a cyano-functional group. Indeed, the molecule is actually ethyl cyanoacetate is the molecule. Now having got the structure, one can go back and interpret this molecule. The OCH2CH3 appears as an ethyl group signature, which is a quartet above 4 ppm and a triplet around 1.5 ppm or so. And this CH2, which is a di-substituted CH2, one of the substituent is a cyano-functional group, the other substituent is a carbonyl functional group. So that appears as a singlet around 3.5 ppm or so. If you look at the degree of unsaturation, which turns out to be 3 for this molecular formula, you can see there are 2 pi bonds of the cyano-functional group and 1 pi bond of the carbonyl functional group contributes to the degree of unsaturation, which is 3 in this molecule. This is an interesting example of a carboxylic acid. One can readily identify this as a carboxylic acid because of this peak here. Actually, the spectrum is recorded only from 0 to 7 ppm. Whatever was above the 7 ppm is folded over and recorded in the same region, but it is indicated very clearly that the delta value of this particular hydrogen is 11. Such a very highly de-shielded hydrogen could be only due to carboxylic acid. So the carboxylic acid hydrogen of one hydrogen integration would correspond to COOH. Then you have a CH functional group because it is a 1 hydrogen intensity, a CH2 functional group because of 2 hydrogen intensity, and a CH3 functional group which is because of a 3 hydrogen intensity of this. The multiplicity here is a triplet, the multiplicity here is a quintet, and the multiplicity here again is a triplet. So the compound is probably CH3, CH2, CH, which is di-substituted. One of the substituent could be bromine from the molecular formula, you can see that. The other substituent could be COOH. So it is a fairly simple molecule. Alpha bromo butyric acid is the molecule. Now having got the structure, you can go back and interpret the spectrum. The COOH appears as a singlet. The CH, which has adjacent 2 hydrogens, appears as a triplet because it is di-substituted, connected to both electronegative bromine as well as electron withdrawing COOH group. It comes around 4.3 ppm or so. This CH2, which has adjacent 4 hydrogen, there are 3 hydrogens on the CH3 and 1 hydrogen on the CH. Accidentally, because of the free rotation of the carbon-carbon bonds, the J value of this hydrogen to the CH2 and these 3 hydrogens, the CH2, will be essentially identical. So it is as if you have 4 hydrogens adjacent to the CH2. The molecule is, the CH2 group is split into a quintet. So you can see here a quintet 1, 2, 3, 4, 5, 6, 5 line intensity is what you see in this particular signal. Terminal CH3 is split by the CH2 and it appears as a triplet around 1.2 ppm or so. This is a spectrum of a simple hydrocarbon molecule, namely paraxylene. Paraxylene is highly symmetrical. It has a plane of symmetry, vertical plane of symmetry, as well as a horizontal plane of symmetry. Therefore, the 4 hydrogens of the aromatic unit are identical chemically, so it appears as a singlet of 4 hydrogen intensity. The 2 methyl groups are also equivalent, chemically equivalent, so a single peak of 6 hydrogen intensity is what is seen for this molecule. It's a fairly simple spectrum to interpret. Now let us ask ourselves a question and try to solve this problem. This is the spectrum of dimethyl cyclopropane dicarboxylate. But which isomer of dimethyl cyclopropane dicarboxylate is not given in the question. That is the question we would like to address in this particular thing. What is important to notice in this spectrum is that there are 4 chemically different hydrogens in this molecule. There are 4 chemical shift values associated with this spectrum. One corresponding to 3.64, which appears to be a singlet here, and another one corresponding to 2.02, which appears to be a multiplet. Then one more signal around 1.62, which appears to be a multiplet, and another signal at 1.2, which appears to be a multiplet. Since the multiplicities are not clearly seen in the spectrum here, the expansion is shown. In other words, this is a multiplicity of this particular signal, and this is a multiplicity of this signal here, and finally this multiplicity corresponds to the signal which is around 1.2 ppm. We will come back to the multiplicity little later, because it is not important to identify the multiplicity at this point of time to solve this problem. What we need to identify is see how many isomers are first of all possible for the dimethyl cyclopropane dicarboxylate. Of the possible isomer, which one will have 4 different types of hydrogen in terms of the 4 different chemical shift value that it offers in this particular spectrum. Now these are the possible isomers of dimethyl ester of cyclopropane dicarboxylate. Now the E group is essentially COOMe group. Just for convenience sake, I have represented the COOMe as the E group here. So this is a geminal diester, this is a 1,2 cis diester, and this is a 1,2 trans diester. These are the 3 different types of isomers that is possible for the dimethyl cyclopropane dicarboxylate. Now if you take the geminal diester and look at the number of spins that you have, these are the 4 hydrogens in the molecule. So we need to identify whether all these 4 hydrogens are same or different. From the symmetry perspective, symmetry point of view, if you look at, the molecule has a plane of symmetry passing through this particular carbon and bisecting this particular carbon-carbon bond, and such a plane of symmetry would put this hydrogen and this hydrogen into mirror image relationship. So the 4 hydrogens are essentially identical in this molecule in their chemical environment. From the substitution criterion also one can find out, irrespective of whichever hydrogen is substituted by a chlorine or a bromine, you will essentially end up with the same compound, which is the bromo derivative of the dimethyl cyclopropane. So one can either use a symmetry criterion or substitution criterion to come to the conclusion that this molecule is of the type A4. In other words, all the 4 hydrogens are identical, chemically equivalent in nature. Therefore, this cannot be responsible for the spectrum we saw in this. This spectrum is not due to this particular compound, because this would essentially offer a singlet for all the 4 hydrogens because they are chemically identical hydrogens. Now come to this particular example. This is a cis vicinal dimethyl cyclopropane dicarboxylate. Now this molecule also has a plane of symmetry passing through this particular carbon and bisecting the carbon-carbon bond bearing the ester functional group. So that puts these 2 hydrogens to be identical with respect to each other. In other words, these 2 hydrogens are chemically equivalent with respect to each other. However, if you take these 2 hydrogens here, these 2 hydrogens are not chemically equivalent, because one of the hydrogen is cis to the ester 2 esters, the other hydrogen is trans to the 2 esters. So geometrical relationship between these 2 hydrogens and the ester functional group are very different. Therefore, this would correspond to either an ABC2 type of a system. In other words, this is A, this is B, and these 2 are the same, so it is C2. It could be either an ABC2 or an AMX2, ABC2 or AMX2, depending upon what is the difference in the chemical shift value between the various hydrogens in the molecule. If the chemical shift differences are very close, then you would call it as a ABC system. If the chemical shift differences are very vast, then you would call it as a AMX system, giving alphabets which are different alphabets, for example, for the vastly different alphabets compared to ABC system. So this would essentially give 4 signal, 1 signal because of the methyl group of the ester, 1 signal because of the CH2, the 2 hydrogens which are the ester connected to the ester carbon, and this CH2 which are the 2 hydrogens are different from each other. So this would essentially give 4 signals, including the ester signal. And if you look at this particular compound, here there is no plane of symmetry. However, there is a C2 axis of symmetry passing through this carbon and passing through the middle of the carbon-carbon bond bearing the ester functional group. So if you look at this molecule, these two hydrogens are C2 symmetric with respect to each other, and these two hydrogens are also C2 symmetric with respect to each other. That makes these two hydrogens equivalent in terms of the chemical equivalence. Similarly, these two hydrogens are also chemically equivalent in this molecule. So at the best, one can describe this to be a A2B2 or a A2X2 system. So it would give only two signals of the cyclopropyl carbons and one signal corresponding to the methyl signal. In all the three isomers, the methyl of the ester would appear only as a singlet because the ester groups are identical in all the three structures of these isomers. So the conclusion is that it is the cis isomer which is responsible for the three signals that you are seeing as multiplets is essentially due to this particular isomer. Now let us try to interpret the multiplicity of this particular spectrum. Now let us take the example of HC. HC is two hydrogens which are attached to a carbon bearing the ester functional group. Most likely these are the two hydrogens which will come at a higher delta value of around 2 ppm or so, which is having a multiplicity of doublet of a doublet. You can see 4-line pattern here. The chemical shift, the value is 2.2. The coupling constant values are already given here. This is 8.5 and 6.7. So this corresponds to 8.5 and this corresponds to 6.7 or so in terms of the two coupling that it can have. So what is this doublet of a doublet due to? These two hydrogens in the absence of any coupling partner would appear as a singlet because they are chemically equivalent. Then they can couple with the trans hydrogen which is a HA hydrogen. So the JAC is one coupling constant and JBC is another coupling constant. So HA will split the signal of these two hydrogens into a doublet, and HB will in turn split the doublet into further doublet, so causing a appearance of a doublet for the HC. So this is explained easily by HA splitting it into a doublet and then HB further splitting it into a doublet. So doublet of a doublet is the signal that you see for this. Now let us take the example of HA. HA is trans, or in other words the dihedral angle between HA and HC is about 180 degree. This is anti or trans with respect to each other. So that is probably having a higher J value compared to the cis coupling, which is the HB-HC coupling, which would probably around 6.7 ppm or so. Now the multiplicities of HA is probably the next one having the higher delta value of about 1.62 ppm or so. And if you look at the multiplicity of this, it would be split into a doublet by HB, and it will be split into a triplet, further into a triplet by these two hydrogens which are HCs. So HA is split into a doublet by HB, which is further split into a triplet by HB. So it should be a doublet of a triplet. Doublet of a triplet should have 6 lines. You can actually see 1, 2, 3. This is one triplet. Another one is this one, and this one. You can see overlapping doublet of a triplet in this spectrum. Similarly, if you look at HB also, it will be split into a doublet by HA, and it will be further split into a triplet by HC. So again another doublet of a triplet is what should be seen. So you can once again see two overlapping doublet of a triplet is in this particular case. So HA appears as a doublet of a triplet, HB appears as a doublet of a triplet, HC itself appears as a doublet of a doublet. The two ester functional group which are COOMe appears as a singlet around 3.64 ppm as a intensity, highly intense signal here because of the 6 hydrogen intensity. So the integration wise also, if you look at the HC which are 2 hydrogen, the integration is twice as big as the HA and the HB. So this is 1 hydrogen intensity, 1 hydrogen intensity, 2 hydrogen intensity, and this is 6 hydrogen intensity, which satisfies the spectral pattern. Therefore, out of the 3 possible isomers, it is possible to easily distinguish them based on the NMR pattern. Remember, we picked this isomer not based on the multiplicity pattern. We simply picked this isomer because this would alone give the 3 signals for the cyclopropyl hydrogen. The other 2 will not give the 3 signals. One gives a single signal, the other one gives 2 signals, for example. That many number of chemically non-equivalent hydrogens are there. This is the only isomer which has 3 different chemically non-equivalent hydrogens, which is corresponding to the spectrum that one sees, and hence the assignment is the correct assignment. Now let us identify this particular compound. This is a fairly simple compound. You can see here 5 hydrogen intensity on the aromatic region of a signal that you see would correspond to a monosubstituted phenyl derivative. Then a quartet and a triplet is seen, so this should be ethyl groups. So most likely the compound is ethyl benzene, and that's what is seen in this particular spectrum. This is a spectrum of ethyl benzene. This is a spectrum of acetylene, which is 1,3,5-trimethylbenzene. 1,3,5-trimethylbenzene is a C3 symmetric molecule. So all the 3 methyl groups are identical. So the 9 hydrogen intensity that you see here for the singlet corresponds to these 3 methyl groups. And there are 3 hydrogens in the aromatic ring which are also chemically identical, and that appears as a singlet of 3 hydrogen intensity. So you have a 1:3 ratio of the intensity area under this peak is about 1/3 of the area under this peak, corresponding to mesitylene structure. Oh, let us consider this example, which is an illustration of diastereotopic hydrogen adjacent to a chiral center. This is actually ethyl mandalate is the compound. Mandelic acid ethyl ester is what is shown here. This particular center is a chiral center in mandelic acid. As a result of that, these 2 hydrogens of the methylene of the ethyl group here, the CH2 of the ethyl group, the 2 hydrogens are diastereotopic in nature. How do we know that it is diastereotopic in nature? If it is a simple ethyl group, you would always observe a quartet and a triplet for the signals of the CH2 and the CH3, like we saw in the earlier examples. However, in this particular case, the CH3 does appear as a triplet. However, the CH2 is a fairly complex multiplet is what is seen here. Now, this particular hydrogen, which is the benzylic hydrogen and also attached to 2 electron withdrawing functional group, comes around 5 ppm or 5.1 ppm or so as 1 hydrogen intensity. Now the CH2 you can see is a fairly complex multiplet is what is seen. In the next slide, the expansion of this particular region is shown. And this is the expansion of the region corresponding to the HA and HB. Both HA and HB come in the same chemical shift region. If the HA and HB are truly diastereotopic in nature, then HA will split HB into a doublet. Similarly, HB will also split HA into a doublet. So what you should see is a 4-line pattern for the HA and the HB. This 4-line pattern will be further split into a quartet because of the adjacent 3 hydrogens of the methyl group. So essentially one should see a quartet of a doublet, which should be 16-line pattern. If you count here, starting from here, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. There are 14 signals that are 14 lines are seen in this particular case. Out of the 14, it should have been a 16-line pattern. Out of that, 2 lines are accidentally merging with each other, resulting in the overlap of the 2 signals, reducing the number of signals seen to be 14. So this is actually an example of a diastereotopic hydrogen being split with each other. The geminal splitting is what is responsible for the multiplet. So the HA and HB appear as a doublet of a doublet, which is further split into a CH3 group into a quartet. So doublet of a quartet is what is actually seen for the ethyl group. So this is an example of a diastereotopic hydrogen splitting itself each other. Now let us take the example of Croton aldehyde. In this particular example, the hydrogens are color coded for convenience. If you take the aldehyde hydrogen, which is this particular hydrogen, that comes around 9.5 ppm or so. This is a 100 MHz NMR spectrum, so this is expressed in hertz. So if you just divide it by 100, you will get the parts per million. This is about 9.55 ppm is the chemical shift value of the blue hydrogen, which is the aldehyde hydrogen, which is shown here of 1 hydrogen intensity. This has an adjacent vicinal hydrogen, which is this magenta hydrogen. So it undergoes a spin spleen interaction with the magenta hydrogen, and as a result of that, it is about doublet multiplicity is what is seen here. Now if you take the alpha hydrogen and the beta hydrogen, namely the magenta hydrogen and the brown hydrogen, because of the electron withdrawing nature of the carbonyl functional group and the resonance that is associated with the double bond being conjugated with the carbonyl functional group, this would be an electron deficient carbon. The beta carbon is always an electron deficient carbon in alpha beta unsaturated system. So electron deficient carbon bearing the hydrogen will have less electron density. So between these 2 hydrogen, this will have a higher delta value compared to this particular hydrogen. So the higher delta value, this comes around 7.7 ppm or so in terms of the chemical shift value. What would be the multiplicity of this hydrogen? This has adjacent hydrogen, which is a trans hydrogen. This trans hydrogen will split this into a doublet. So you do get a doublet, and this doublet is further split into a quartet. So what you should see is a doublet of a quartet. So what you should see is a 8-line pattern. Start counting from here: 1, 2, 3, 4, 5, 6, 7, 8. What you are seeing is an overlap quartet. You can see one quartet, signal number 1, signal number 2, signal number 3, and signal number 5 corresponds to one quartet. Signal number 4, signal number 6, 7, and 8 corresponds to another quartet. So overlapping quartet of a doublet is what is seen for the multiplicity of this hydrogen, which is the brown hydrogen. In the case of magenta hydrogen, it is a little more complex because it has two coupling partners, one trans coupling partner, the other one is a vicinal coupling partner. So this will be split into a doublet by this, and further doublet by this blue hydrogen. So this would be a doublet of a doublet. Further it will be split by the allylic hydrogen, which is the CH3 hydrogen, into a quartet. So doublet of a quartet is what you should see. In fact, 16-line pattern is what you should see. You can actually see two sets of quartet, one set of quartets here, another set of quartets here. So the four quartets are essentially seen as a doublet of a doublet, which will give 4 lines, and 4 lines are further split into a quartet by a CH3 functional group. So this is essentially the spectral feature of the magenta hydrogen in terms of the multiplicity pattern of the hydrogen. Now finally let us come to the CH3. CH3 is coupled to both the the vicinal hydrogen, which is this brown hydrogen, as well as the allylic hydrogen, which is the magenta hydrogen. So it will be split by brown hydrogen into a doublet, further split by the magenta hydrogen into a doublet. So it should see a doublet of a doublet. The 4-line pattern that you see for methyl group is essentially a doublet of a doublet pattern is what you are seeing in this particular molecule. Now this is very similar to the paraxylene molecule. It is a symmetrically disubstituted derivative. The two ethyl groups are identical, so it gives only one set of signal, one quartet and one triplet for both the ethyl groups. So if you look at the integration intensity here, you take the height of this particular integration and height of this integration and height of this integration. This will be exactly 2:2:3, corresponding to 2 of the CH2, 2 of the aromatic hydrogen, and 3 of the methyl group hydrogens. So although there are 2 methylene group, it appears as a single quartet because of the chemical identity. These two CH2s are chemically identical because of the symmetry of this molecule. So you see only one quartet and one triplet for both the ethyl groups. Of course, the aromatic ring is a highly symmetrically substituted aromatic ring. So all the 4 hydrogens are chemically identical, and it just gives you a singlet. So the diethyl terephthalate molecule gives essentially a very simple spectrum of a quartet, triplet and a singlet corresponding to the CH2, CH3 and the aromatic hydrogens of the molecule. Now let us see what happens if you make the ortho isomer. In other words, instead of terephthalate, if you just take phthalate, this molecule is less symmetrical compared to the terephthalate. This has only one plane of symmetry instead of 2 planes of symmetry. So if you look at the aromatic hydrogen, there are 2 sets of aromatic chemically non-equivalent hydrogen. One set corresponds to the one adjacent to the ester functional group. The other one corresponds to meta to the ester functional group. So these 2 hydrogens are chemically equivalent, and these 2 hydrogens are also chemically equivalent, but they are chemically distinct from each other. So you can see a complex multiplet pattern is what is seen here, because the spin system is A prime, B prime. So this is a 2-spin, it's actually a 4-spin system, 2 chemically equivalent but 4 magnetically non-equivalent spins is what you are having. That is why you get a complex. We will deal with these complex situations a little later. For the time being, let us come to the conclusion that the more symmetrical the structure is, the NMR pattern is much simpler compared to a less symmetrical structure will lead to more complex NMR spectrum. In this particular isomer also, the ortho isomer also, the 2 ethyl groups are identical in terms of their chemical nature. So it essentially gives one set of quartet and a triplet for the 2 ethyl groups of this molecule. The integration again would be 2:2:3 is the integration, which is actually 4:4:6 in terms of the number of hydrogens that you have in this molecule. Now if we take this simple molecule, This is a monosubstituted benzene derivative. So in the aromatic region you have signals between 7 to 7.5 ppm as 5 hydrogen intensity, and the CH2, which is a red CH2, which is the benzylic CH2, comes around 2.8 or 2.9 ppm, and this CH2 which is attached to oxygen comes more than 3 ppm. You can see the difference between the chemical shift values of these two types of methylene. So this methylene is a triplet because of adjacent 2 hydrogen. Similarly, this methylene is also a triplet because of the adjacent 2 hydrogen. So two triplets are seen for this molecule. This methylene hydrogen is the methylene carbon is also attached to an oxygen. That is why the chemical shift value of this is much higher than the chemical shift value of the benzylic hydrogen. Finally, the OH hydrogen is a D2O exchangeable hydrogen, so it appears as a broad signal around 2.2 ppm. This can again be identified by deuterium exchange experiment by adding a D2O. Upon adding D2O, this particular signal will vanish, indicating that this is an exchangeable hydrogen. This is a molecule with CH2, CH2, CH2Br. So that means this CH2, which is the blue CH2, has 4 coupling partners. So it should be a quintet, and you do see a quintet here. 1, 2, 3, 4, 5 line intensity is what you are seeing here. The other CH2 simply appear as a triplet. This is a triplet because of 2 neighboring hydrogen. This is also a triplet because of 2 neighboring hydrogens. The 2 triplets are seen. Chemical shift wise, the one that is attached to bromine has the highest chemical shift value, around 3.5 ppm. The one attached to the benzylic will be the next one, which is around 2.8 or 2.9 ppm. Finally, this one which is flanked between the two CH2s will be the least chemical shift value, around 2 ppm or so is what's seen. The aromatic signal, you can see 5 hydrogen intensity of multiplet is what is seen here in this particular spectrum. Let us take this particular example. This is a pyridine derivative. Now the pyridine derivative, you can see here, this is amino substituted pyridine derivative. All the 3 hydrogens in the aromatic ring are non-equivalent in nature. Chemically they are non-equivalent in nature. So if you take this particular hydrogen, it will be split into a doublet by this ortho hydrogen, another doublet into an ortho hydrogen, which is this particular hydrogen. So this should actually appear as a doublet of a doublet or a triplet if the ortho coupling happens to be identical. In fact, the ortho couplings are nearly identical. So this hydrogen, which is in the 4th position, essentially appears as a triplet of 1 hydrogen intensity. And this hydrogen essentially appear as a doublet and a doublet. So you see 2 doublets also for the 2 types of 3 and 5 hydrogens. 3 position and 5 position hydrogens come in this region as doublet each. Finally, the NH2 appears as a broad signal. We have already seen NH2 as a broad signal in the propionamide. It's a very similar case. It is D2O exchangeable because it is exchangeable hydrogen. Finally, the CH3 appears as a singlet in the spectrum, which is shown here. So what we have seen in this module is a number of proton NMR spectra and the interpretation of the proton NMR spectra to make yourself familiarize with the chemical shift values and coupling constant values. We still have not seen an example where how to calculate the chemical shift and the coupling constant value from the spectrum, which we will see in the next module. Thank you very much.